Hey everyone, so this is the next part of the forces unit where we're going to talk about Newton's three laws of motion. So you may have heard the story about how Isaac Newton was hanging out underneath an apple tree, got hit on the head, and instead of thinking things like, ow, that hurt, he started asking himself, I wonder why objects move differently. And this ended up leading to what we consider the foundation of all of not only forces, but just physics in general. It leads to what he ended up calling his three laws of motion. These rules that govern everything about how and why objects move. In order to show how important these three laws are, we end up actually calling this part of physics Newtonian physics, in comparison to uh, later on when we end up getting to what we later call modern physics, that separate into things like quantum mechanics and relativity, special relativity, and all that stuff, to differentiate that from this stuff. So Newton's three laws act as a foundation that govern every other rule, law, equation, and concept that we're going to be talking from here on out. So keep that in mind. This is extremely important. How useful and critical these three laws are. And in fact, a lot of times when you're doing your little explanations of, for the questions, you're going to have to try to incorporate Newton's three laws in there in some way because they're that important and they can be used to explain a lot of different phenomena. All right. So we're going to start off with the very first law, which explains essentially why objects move the way they do. That's really the whole point of this. Now, there's a lot to unpackage with this first law. It's for the most part a very basic law, but there's so many other components part of it. Now, the law is split into two, and I think most of you have probably heard his three laws at some point. You just may not have known that they were his three laws. Now, the first part of this law is an object at rest tends to stay at rest unless acted upon by an unbalanced force. And then the next part is the an object in motion tends to stay in motion, moving at a constant velocity unless acted upon by an unbalanced force. So this leads into what he essentially calls, or what we end up calling, the law of inertia, that uh, objects don't move unless you force them to move. That objects won't just randomly start moving out of nowhere. There has to be a force acting on them in order to cause them to not only move but change their motion. Objects will naturally want to keep doing what they're doing. If an object was initially at rest, it's going to stay at rest unless you force it to move. If an object is moving, it's going to continue moving in a straight line unless you force it to deviate from that line, either by changing its speed or changing the direction it's moving. Now, this one's actually a really interesting thing because the second part of this law is extremely hard for us as humans to conceptualize and understand and wrap our heads around, mainly because of the fact that there is an invisible force constantly acting on objects that make it hard to recognize that this is true, and that's friction. Friction's always acting on objects, slowing things down. If you push an object on a table and you no longer have a force applying to it, you'll notice that the object starts to slow down. So how does that contribute to this equation? It's because this law. It's because of the fact that there's a friction force acting on it, slowing it down. If it wasn't for friction, that object would continue moving forever and ever, moving in that straight line. And we can see this when we actually start making surfaces slippier. All right, we decrease the amount of friction acting on it. Maybe instead of doing it on a table, we do it on a sheet of ice, very smooth ice, or Teflon, something that is very slippery. If we do that, we do notice that the object will start traveling further and further without slowing down, following this law. And we also see it, we actually do see it in space. But it is pretty interesting that Newton was able to understand this at such a fundamental level so far back in time, where he wasn't able to test this in space in the absence of friction. And probably even before the concept of friction was even a thing. So the going back, what we said about inertia, this, like I said, this law, we kind of call it the law of inertia. The word inertia just refers to an object's resistance to the change in motion. That's what inertia means. So an object with high inertia is harder to move. That's the payoff. That's the higher the inertia, the harder it is to move. The lower the inertia, easier it is to move. Now, as far as we're concerned, inertia is just a fancy way of saying mass. So objects with higher mass have high inertia. Easy enough, right? If an object is very massive, then it requires a lot more force to change its motion, not just to get it to move, but to change its motion, right? If an object's at rest and you have a very massive object like a giant car, it's going to require a lot more force to get it to move than if you had a little bit of a little itty bitty ping pong ball. Um, so, oh, this is one of the reasons why we use wrecking balls to demolish buildings and we use anvils to bend metal, mainly because of the fact that those two materials have very high inertias. For the wrecking ball, at least, with its very high inertia, it basically means that it it has so much mass, so much inertia that it requires a significant force to stop it when it's in its swing. So when it comes up to that wall is incapable of providing the necessary force to stop or impede the motion of that wrecking ball, resulting in the wrecking ball just passing right through and breaking through the wall, which is why the wrecking ball is such a good material or design for demolishing buildings. Same thing with the anvil. For those who don't know, blacksmiths will use these giant metal anvils in order to help bend and shape metal. And one of the reasons is because when they're hitting onto the metal, they can't have the surface constantly moving and jumping. If they're hitting down on something and you have a surface like a table that's really light, that table will move and adjust as you kind of hit down on the metal. So you need this really really heavy anvil so that it has a very high mass and it requires a significantly high force before it begins again changing its motion, getting out of that at rest state. This is just a quick commercial about the idea of replacing a wrecking ball with a stuffed animal. These are all examples of the concept of inertia. It's basically this picture. The importance of this picture is kind of showing why seatbelts are important. When you're in the car and you're driving at the same, you're in the car and the car's moving. You are moving with the same speed that the car is moving. So you are traveling with some speed. When the car comes to a stop, because of Newton's first law, your body is going to want to keep moving forward. The only thing that's going to stop it from moving forward is having it some sort of unbalanced force acting on you. Without a seatbelt, the unbalanced force would be the steering wheel hitting your face, the glass windows hitting your face, or the brick wall in front of you. So something's going to act as the thing that stops you and applies the force. You just want something that's comfortable, like an airbag or a seatbelt. Those things will actually act as the outside force to stop the movement, the forward movement, while you're in the car. So yeah, these are all kind of the ideas of Newton's first law. So here's the first question. Pause the video itself, and we'll go to the second. All right, really easy one. It just wants to know which one has the greatest inertia. Again, inertia is just a fancy way of saying mass. So boom, this one 4 kilograms. Now you'll notice that they have these speeds in here. The reason they have this is because inertia has a very similar definition to another term that we're going to talk about much later, which is called momentum. And momentum takes into account both the mass and the velocity. So this is supposed to be a trick question where they want you to think that you have to find the momentum when really you're just looking for the mass. And it turns out that they always set up this problem so that the object with the highest momentum typically has the lowest inertia and vice versa. Right? Now, there's another part to this law that's extremely important to take, and it's the concept of equilibrium. So, equilibrium, as far as we're concerned, is the state of balance. You probably learned that in chemistry with like chemicals, it being in equilibrium or whatever, homeostasis. Um, if you notice, the law said that objects at rest will tend to stay at rest, or objects in motion will tend to stay in motion unless acted upon by an unbalanced force. So we can then say if the forces are balanced, then the object will continue doing what it's doing and will not change its motion. I.e., if the forces are balanced, we can say that it's in a state of equilibrium, of balance, and that the object will either be at rest or traveling with a constant velocity. or in other terms, not accelerating. And that's the key thing. Objects that are not accelerating are in a state of equilibrium, and objects in equilibrium are in a state of not accelerating. It's important to keep in mind that these two things go hand in hand. The reason why this is important is because a lot of times they'll say the word equilibrium, and you have to make the connection of not accelerating. And when they say not accelerating, you have to make the connection of equilibrium before you can proceed with the question, right? If you don't make that connection, some of these questions will end up becoming a lot harder. But it becomes pretty straightforward. You know, you'll see the word equilibrium a lot enough to kind of realize this. But the one thing that kind of trips people up is they typically think equilibrium with the phrase at rest, and they always forget that constant velocity also matters. See, it makes sense for an object that has balanced forces to be at rest. You can imagine pushing on a table with two people going in opposite directions. They're pushing with the same amount of force. The object doesn't move. Okay, that makes sense. But it's a lot harder to visualize an object that is moving while having these balanced forces. But keep in mind, it is true. The objects that are moving at constant velocity do have balanced forces, mainly because you have cases like friction, where if you're pushing on an object and it's moving at a constant velocity, it's because you're balancing out the friction on it. Try not to overthink it, but keep in mind that equilibrium goes with both terms, right? So if you know an object's in equilibrium, you don't necessarily know whether it's at rest or moving with a constant velocity. It could be either or. So you need to have more information before you can, you know, correctly identify which of those two motions uh, it, it's moving in. But if you know it's at rest, or if you know it's moving at a constant velocity, you know it's in equilibrium. All right. This also leads into this phrase called net force. Net force is essentially the total force acting on an object. Keep in mind that force is a vector, so direction matters. So when we say it's the total force acting on it, we mean that it's the vector sum, right? So if you have two forces going in the same direction, you add the forces. If they're going in opposite directions, you subtract the forces. So when we have an object that that is experiencing forces, what we're going to want to do is look at the net force in the two directions, the x direction and the y direction. What we like to do is, you call them like fx or fy or f net x and f net y. Remember, try not to overthink the subscripts. You can put the subscripts however you want to make it the most sense for you. Um, so if an object's in equilibrium, it means in both the x and the y direction, the net force is equal to zero. So the forces are balanced. So the forces in the x direction are balanced, the forces in the y direction are balanced. Now, if the forces in the x direction don't equal to zero, then the object's not in equilibrium. All right. And the same thing is true in the y direction. So if one of these directions, either the x or the y, is not the forces that add up in that direction don't equal zero, then the net force is going to be equal to that. And like I said, it's not going to be in equilibrium. If there's an unbalanced force in both x and y, then not only is it not in equilibrium, but in order to find the net force, we're going to have to do Pythagorean theorem. The x and y act as the components for the net force. Honestly, that last one doesn't really come up too much. Typically, the problems that you're going to see, objects will have an unbalanced force in pretty much only one of the two directions. And it's a lot of cases it's going to be in the x direction. I don't want to make it sound like it's always going to be the case there, because there are cases where the object's moving vertically with unbalanced forces, and you want to be aware of that. But a lot of times we have objects moving on horizontal planes, sliding across horizontal surfaces. So it's the horizontal forces that will usually be unbalanced when the object's not in equilibrium. Right? But the key thing is to realize this idea of looking at all the forces acting on the object, again, keeping the x and y directions separately, and trying to think about what it means to be in equilibrium and what that means for the forces. Again, knowing this term equilibrium and knowing that it occurs in the states of being at rest or moving with a constant velocity is critical to approaching these problems. All right, so here's the first question. Pause the video, works up, and we'll go in a second. All right, so here it wants us to determine which objects are in equilibrium. we pretty much want to go through each of these choices and see which one could be it. Uh, choice A says a ball dropped from a building. This one is definitely not it because we know objects that are falling in the air are being affected by Earth's gravitational acceleration. Their velocity changes. Therefore, this is not in equilibrium. Same thing for a ball being thrown in the air. It's still in the air, still being affected by Earth's acceleration due to gravity, so it's still not in equilibrium. C, we kid rolling down a hill with increasing speed. Again, because the velocity is not constant, this object is accelerating and therefore not in equilibrium. D, car on the highway on cruise control. If you don't know what cruise control is, it basically allows you to set your speed and the car will maintain that speed the entire time. So D is in equilibrium. The velocity of this car is not going to change during its ride on the highway. E, the book sliding to a stop. Again, it changes its velocity, not in equilibrium. F, a stoplight hanging from a cable. The stoplight isn't moving, so it's going to be just at rest there, like typical stoplights. Therefore, it is in a state of equilibrium. The forces acting on it are gravity pulling it down, and there's a tension force pulling it up, and those two forces will be balanced. Now, G is going to be an interesting one. The Earth orbiting the sun at a constant speed. A lot of people might think that this would mean the object's in equilibrium, but the answer is no. G is not in equilibrium. And the reason is because the statement is that the object has to be traveling with constant velocity, not constant speed. Constant speed just means that the value of the velocity isn't changing. But as I mentioned before, it has to be continually moving in a straight line. And when the Earth orbits the sun, its velocity changes because the direction of its velocity is constantly changing. So Earth orbiting the sun is constantly accelerating and is not in a state of equilibrium. Right? So it's only D and F that are the proper answers. Here's the next one. Pause the video, work cell phone, go in a second. All right. Now, one thing that's important to note is that for a question like this, again, we use the phrase that the forces are balanced in equilibrium. A lot of you are probably going to say they're equal, and I'll usually try to correct you and say balanced, mainly because of the fact that I want you to keep in mind that it does that all the forces acting in all the directions don't have to all equal each other. They just have to balance in certain ways. For example, here we have two newtons going up, two newtons going down. Those two are balanced. We have 5 going to the right, 5 going to the left. Those are balanced. Keep in mind, though, that there could be more forces acting on an object. For example, if I slightly change this so that instead of having just a single 2 newtons going up, I also had a 3 newton force going up, then this object would be in equilibrium because the forces going up are balancing the forces going down. And the forces going to the right are balancing the forces going to the left. So again, the forces don't have to all be equal, they have to balance out. So the answer was 2 because that wasn't there. Like I said, it's extremely important that you draw the FBDs. I mentioned this in the previous video, but it's important that you draw the FBD in order to actually be able to visualize whether the object's in equilibrium. Because a lot of times you have a multitude of forces acting on an object, and it can be hard to keep track of which forces are going in what direction and what they're equal to. Doing the FBDs kind of really helps keep everything organized and helps you solve the problem. I cannot stress how important FBDs are. And like I said, you should always kind of keep in mind what forces are always there. Like, for example, the force due to gravity or the weight of the object is pretty much always acting on the object. There's very few cases where it's not acting on an object. And, it's always, at least when you're on Earth, acting downward. And then you always, typically have a contact force like a normal force. Again, this one isn't always there, but it's very commonly there. As long as you're touching a surface like the floor or the wall or anything like that, there's going to be a normal force. So knowing that these two forces are very commonly in most problems is very important. All right, so we'll leave it there. That's it for Newton's first law. Like I said, there was a lot to unpackage, even though the law is pretty bare bones. Now, one thing I do want to point out is You don't need to know word for word what the first law is. You just need to know the idea that it